Good day, grade 11s, and welcome to the first video of the grade 11 climate and weather series. I'd like to say thank you for tuning in, and I hope this will be of great benefit to you. Now, going to our CAPS document, you can clearly see that this is the very first concept that we'll be covering. So, under the subtopic of the Earth's energy balance, we have the first concept, which is the unequal heating of the atmosphere, right? Latitudinal and seasonal. So these are two reasons why the Earth receives different amounts of insolation throughout the year. Okay, we have a latitudinal reason and we also have a seasonal reason, and we'll see how that occurs, right? And then the next thing that we are going to cover in this video is the significance of the Earth's axis and revolution around the sun. So here we're simply going to talk about how seasons occur, right? So we'll talk about revolution, we'll talk about rotation, we'll talk about the cycle of illumination, we'll talk about parallelism. So there's a lot, guys, to look forward to. So please stick with us as we will cover everything. So we're not going to look at this today, right? The transfer of energy and energy balance. Okay, we'll look at the reason why there is an energy imbalance on Earth. Okay, the first two concepts are reasons why we have energy imbalance, and then the third concept speaks to how this energy balance is then resolved, or how this energy is then balanced. You don't have to worry about that now. We will cover all of that, guys. So, in other words, this is a solution to this energy imbalance, if you may look at it that way, from the energy imbalance to energy balance, right? Okay, so without any further ado, let's get on to it. Right, so the first concept, as we said, guys, is the unequal heating of the atmosphere. Okay, so the atmosphere does not receive the same amount of insolation. Remember, guys, insolation is incoming solar radiation. So, in other words, it is the approaching, or it is the sun's energy. Remember, solar means sun and radiation means energy. So it's the incoming sun energy. Okay, the energy that is coming from the sun. Okay, so we call that insolation. So it's simple, guys. There's nothing more to that. Insolation is the approaching sun's energy. So we're saying that this insolation, or this amount of insolation received, it's not going to be the same in all parts of the earth, right? And we discuss the reason why that's the case. Okay, so the unequal heating of the atmosphere. Some parts of the earth receive more energy, some parts of the earth receive less energy. Okay, so then it becomes an energy imbalance, as I mentioned in the beginning, right? Okay, so first of all, the earth is nearly spherical, right? Okay, it is nearly spherical. It is not exactly a sphere, because if you look at this shape, for an example, you can see that it is much more wider in this dimension than that dimension. So it is much more oval, okay, if you can put it that way. And then that has a lot to do with the Earth's rotation, but we'll talk about rotation later on in the video. So we're saying that the Earth is nearly spherical, and because it is nearly spherical, it receives different amounts of insolation, or the insolation received is unequal throughout Earth. Okay, because now we see that areas that are close to the equator are warm. Okay, so this is what we're talking about, the tropics, guys. The areas that are close to the equator over there. So that's the equator, the center, or that is at the center of the earth, right? So areas that are closest to the equator, we observe that they are very warm, right? And the reason, okay, you have to know the reason. Okay, they can ask you why. Okay, why is the equator warmer than other regions? It receives the most insolation than any other place on earth, right? The equator, right at the center. Okay, so the reason why the equator is warm is because it receives direct sun rays. Okay, it receives direct or perpendicular sun rays. What do we mean by that? Okay, now let's take a look at this, guys. This is Like for an example, this torch over here, it represents the sun. So this is how the sun illuminates Earth. So by illuminate, I mean this is how the torch or the sun brightens Earth. Okay, so you have the sun's rays, right? So the energy is in the form of rays, okay, or beam, sunbeam. So what we see here is that right at the equator, the sun's rays or the sun's energy hits straight. Okay, I don't know if you guys see that. It hits straight. The sun's rays are perpendicular like that. Okay, so let me zoom in again so that you can see this clearly, right? Right, so at the equator, the sun's rays or the sun's energy or the sun's radiation is perpendicular or is direct, or we can say that it hits at the highest angle, okay, because this is 90 degrees, right? So if I could draw a line here, so that is the sun's rays, and draw another one like over there, okay, so that would make 90 degrees, right? So 90 degrees at the equator, so that is quite high, right? 90 degrees. So that's why we say that the sun's rays hit perpendicularly, or they strike the earth's surface at the equator perpendicularly or directly. And so if the sun's rays hit a particular area perpendicular, so it's overhead, okay, sometimes they use the word overhead. They say the sun is overhead, okay, it's right above it, okay, it's like right on top of you. The sun is striking you directly, so that's what we mean there. So the reason why the equator is warm is because, number one, the sun's rays strike the surface at the equator perpendicularly, or the sun's rays are direct at the equator. That's your reason there. The second reason is because at the equator, these sun's rays are concentrated on a small area. Now, if you think about this, guys, the distance, for an example, from here all the way to there is much shorter than the distance from there all the way to there, right? All of these sun's rays are concentrated in this particular small area right over there, okay? In this particular area over there. So if I have a lot of the sun's energy concentrated there, a lot of the sun's rays hit in this same area like that, of course the energy is intense, guys, right? So that's the second reason there, is that these sun's rays, they are not spread, but they are concentrated over a small area. Okay, this particular area over there, the sun's rays strike this, they are concentrated there. Okay, so now this makes the heat more intense. It makes the sun's energy more concentrated, right? So that's the second reason, guys. Please do not forget these reasons. The first reason is that the equator is warm because it receives direct sun rays. The second reason is that the equator is warm because the sun's rays that the equator receives are concentrated on a small area. So this makes the energy that the equator receives more intense, right? So this means that the equator now receives a lot of intense energy, right? So there's a lot of energy there that is intense at the equator. It receives more energy than it can lose. Remember, guys, the atmosphere can reflect the solar radiation. It can scatter it. It can absorb it, as you learned in grade 10. But there's a lot of energy there that is received. So it receives a lot more energy than it can lose. Okay, because it receives a lot. It's intense energy. So you can sort of imagine that the equator is very hot, right? Very hot because of this intense heat. It receives direct, first of all, sun rays, and it receives concentrated sun rays, meaning which these sun rays are concentrated on a small area, okay? They are not spread over a large area, right? So we're saying that more energy is gained than lost at the equator. Okay, so the equator receives the most heat, right? It receives the most insolation than any other part of the earth, right? So that is very important to note here, guys. Okay, there's a lot of energy at the equator, okay, not in any other place but the equator. So this already says something about the energy distribution, or the amount of energy that the Earth receives as a whole, because a lot of energy is received here at the equator. What about other parts? Okay. So now let's talk about these other parts. Let's talk about the poles, guys. What happens at the poles? So remember, these are your poles. So this is your North Pole, and that is your South Pole, right? So what about the poles? The poles are cold, right? That's where you're going to find icebergs. That's where you're going to find snow, ice. And the reason why it is cold, there's three reasons for that. First of all is that the polar regions receive oblique sun's rays. Okay, oblique sun's rays. So oblique, what do we mean there? We mean at an angle. Now we talked about the angle at which the sun's rays strike the equator, and it was high, right? 90 degrees. But what about the angle at which the sun's rays strike the polar regions? Now let's take a look at this. Okay. Now if you could look closely here, you can clearly see that the sun's rays hit polar regions at an angle that is, let's say, for an example, about 60 or 70 degrees. Okay, so that's an oblique angle, right? So this simply means that the sun's rays hit the surface here at an angle. Okay, you can simply put it that way. It's at an angle. Okay, it is not parallel, it is not perpendicular, it is at an angle, right? So that is what we mean by oblique. It is not direct, it is at an angle, right? And so because the sun's rays do not strike the surface directly there, this means that the sun's energy is not going to be concentrated, right? And so they receive less insolation, the polar regions, because they receive oblique sun rays, okay, or sun's rays that are at an angle. Number two is that the sun's rays here are spread over a wide area. We did look at the equator and we clearly see that the sun's rays are concentrated over a small area. But if you take a look at the polar region, you can clearly see that, okay, uh, the sun's rays are spread over a large area. Okay, so if I may draw that area over there, that's that area over there. Okay, it's spread over a large area, as you can clearly see, guys. That's a large area, and so it's not going to be intense. The heat that is received there, because it is spread over a large area, right? So it is not concentrated. Okay, so that's what we mean there. So that's the second reason why the polar regions are cold, is that the sun's rays are spread over a wide or a large area at the poles. And then the third reason is that you have high albedo snow there. Okay, high albedo. Remember, albedo is the measure of how much an object can reflect the sun's energy back. Okay, so because snow has high albedo, that means it reflects more of the sun's rays that it receives, or more of the sun's energy that it gets. Okay, so the energy that it receives, noting that this energy is already a small amount compared to the equator, this energy is also reflected back. So that's the third reason there. The little energy the polar regions receive, they also reflect it because of the snow, high albedo snow that is present there in the poles. First reason why the poles are cold is because the sun's energy strike the Earth's surface there at an angle, at an oblique angle. That's number one. Number two is that these sun's rays are then spread over a large area, right? Not concentrated over a small area, but spread over a large area. That makes them weak. That makes the energy that they carry weak, right? Third of all is that you have snow there, snow which has a high albedo, so that reflects much more of the energy that is sent or that is received, right? So it's very important that we note that. So this means that here energy, a lot of energy is lost. Okay, the little energy that the poles receive, it is lost, guys. Much of it is lost. So here more energy is lost than gained. Okay, you have little amount of energy that you get, and you reflect it back because of the snow. It's the amount of energy you receive is little because of the sun's rays, that are at an angle, and because they are spread over a large area and so not concentrated, and hence the amount of insolation that is received here is already small compared to the equator, and this little amount of energy is then reflected. Okay, much of it is reflected back, right? Now, so that's why the polar regions are cold, guys. Okay, so you have to be able to explain that. Why are the poles cold? Why is the equator warm, right? It's quite important. So you can clearly see that there's an energy imbalance now because, well, the equator receives a lot of the heat and so it receives a lot of energy, right? So there's high energy at the equator. Okay. So this results therefore in unequal heating. Okay. So that's what we mean by unequal heating or energy imbalance. Okay. Because there's more energy at the equator, less energy at the pole. So that's not equal, right? So there's more energy that is lost here at at the poles than gained. Okay. As of course, and yes, of course, this results in unequal heating of the Earth, low latitudes. Okay, low latitudes, that's your 0 degrees, are warm. Okay, and then high latitudes, that's your 90 degrees. Like in terms of the latitude, guys, this is 90, that is 0. The equator, that is 90, right? So that is low, that is high, right? 90 degrees is larger than 0 degrees in terms of the size of the numbers, right? Low latitudes, equator; high latitudes, polar regions, right? And so we say that the amount of insolation received depends on the latitude. Okay, in which latitude do you stay? Okay, I stay at the equator, and so I receive more insolation. If you stay at the poles, you receive less insolation. So the amount of insolation that is received, number one, depends on latitudes. That is very important to note. Right. Hope you guys get me here. That is very important, guys. Okay. The latitudinal heat difference is due to the sphericity, or is due to the shape of the Earth, that you have latitudinal heat differences. Let's head on to the next one then, which is the importance of the Earth's rotation and revolution. So now Earth's rotation and revolution results in seasons. Okay, we'll talk about that. How seasons occur. Okay, before we get into that, we have to understand Earth's movement. Of course, guys, we live on Earth, right? Earth is a planet, part of the solar system. Okay, so because we do not feel the sense of movement of Earth, people actually still do not believe this. But actually, Earth is not standing still, guys. Earth is not stationary. Earth is constantly moving. Okay, the Earth that we are sitting on is moving, right? It is not standing still. Okay, it does what? It rotates. It rotates on its own axis. An axis is this imaginary line, as you can see, guys. This imaginary line over here. Okay, that cuts Earth into two parts or two halves. So that is Earth's axis. It's an imaginary line. Doesn't mean that you are going to actually touch it. It's an imaginary line that helps us understand Earth's movement. So you have the Earth's axis, which is an imaginary line that passes from the North Pole. Okay, so right over there, that's the North Pole. And as you can see, it goes through Earth to the South Pole, right? Okay, so it's an imaginary line. That is what we mean by the Earth's axis, right? So it's not standing still; it rotates around this. Okay, I've shown arrows here. So these arrows mean that the Earth is rotating around this axis. Okay, now stay with me here. Please stay with me. Okay, so we're saying that Earth rotates on its axis, on its own axis. Okay, rotates around this axis. Now, about the Earth's axis, it's important that we note, okay, it's important that we note that the Earth's axis is not vertical like this. Okay, I just wanted you guys to see that the Earth's axis cuts Earth in half like that, right? Okay, so it's not exactly like this. It is actually 23 degrees away from the vertical. So let me show you, okay? Instead of being vertical like that, the Earth's axis is like that, something like this, okay? It's like this instead of being vertical, like 0 degrees, okay? As you can see, 0 degrees, it's actually 23 degrees, okay? Don't mind that number over there. So it's actually 23 degrees to the perpendicular, right? So instead of being vertical like that, okay, so this is the vertical line. Well, I hope it's vertical. Instead of being vertical like that, it's actually at an angle. Okay, it is actually rotated like that. Okay, it still cuts the earth half like that. Okay, but instead of being vertical like that, it is at an angle. It is tilted. We say that it is the earth's axis is tilted 23.5 degrees away from the perpendicular, right? As you can see like that. Okay, so instead of being straight like that, if you may call it that, it is tilted. Okay, so the earth's tilt, when they talk about the earth's tilt, they talk about this number right here. How much has it tilted? It has tilted 23.5 degrees away from the perpendicular. Okay, while it is doing this, it is actually, as I said, guys, it is rotating, right? It is rotating on its own axis, okay, going around and around and around this earth's axis like that, right? So the earth rotates, considering that the earth's axis is actually tilted, right, 23.5 degrees away from the perpendicular, right? So this is important to note. It's also important to note that the tilt, right? The tilt of the Earth's axis does not change. Okay? It does not change. It will always be 23.5 degrees away from the perpendicular. And this is important to note because the tendency of the tilt or the tendency of the Earth's axis to remain at 23.5 degrees away from the perpendicular, okay, to not change. We call that parallelism, right? So it will maintain its tilt. It will maintain that 23.5 degree tilt throughout, okay, throughout the year. So that's what we call parallelism. It does not change. It does not suddenly become 15 degrees or change to 25 degrees. It stays at 23.5 degrees, guys. So that's what we call parallelism. This is an important term. It could be asked in your test or exam. So please, let's take note of that. Parallelism, that's a new term, right? The tendency of the Earth's axis to remain the same throughout the year, right? So that's what we're saying. So it is rotating while tilted, okay, at 23.5 degrees. Let me actually show you guys. Yeah, there we go. Okay, can you see this? It is tilted, right? Okay, it is tilted because it is not vertical, but at the same time, right, it is rotating. Can you see that rotation? It is rotating while tilted. Okay, can you guys see that? There we go. So that's what we mean. It's important that we are able to visualize this. And I got this actually from Earth Space Lab. So if you want to check that out, please do. Because it is quite difficult to understand the Earth's movement. You're trying to figure out, okay, it is tilted and it is rotating at the same time. How does that look? This is how it looks. Okay, that is exactly how it looks, right? So I hope you guys see this. Okay, there's the Earth's axis going through the Earth, right? As you can see, and it is at an angle. It is not vertical. It is tilted. The Earth is tilted. It is tilted at 23.5 degrees away from the perpendicular, and it is rotating. Right, every day it is rotating, and this rotation is important. Okay, this rotation is important because it is what causes day and night. Okay, the reason why we have day and night is due to this rotation of the earth. Okay, now let me actually just go back there. Now let's take a look at this, guys. So while it is rotating, some parts of the world receive insolation. Okay, they get light, and some parts that are behind, like over here at the moment, they do not get any light. So it is day here and night over there. Okay, and it constantly goes on and on and on and on. So if I would pause this, it would be a day on this side, right, and night on that side. Okay, and this actually goes on and on and on. So half of the earth, so half of the earth, while it is having daytime, the other half of the earth is having nighttime. Okay, I think I should show you a better animation. I'll show you a better animation of that. So we're saying that this constant rotation means that only one half of the earth receives insolation at a time. Okay, so at a time, one half of the earth is receiving the light, and the other half is actually at the shadow, or you can say that it is in darkness, right? So the other half, it is in darkness at a time, right? Because it is constantly rotating. Okay, constantly rotating. So it is not, guys, it is not the sun that is rotating, it is the earth that is rotating, but it looks like it's the sun that is rotating, right? Because from our point of reference, from our perspective, it looks like we are standing still and the sun is actually rotating around us, moving around us, but it's actually the opposite. We are the ones that are rotating, right? And that makes it seem like the sun is actually rotating, right? So I need us to take note of that. Earth is the one that is rotating, not the sun, right? And this rotation means that at any moment, half of the Earth is receiving insolation, right? It is in the light, it is exposed to the light, or it is exposed to the insolation or the energy from the sun. And so this means that it is day. And then the other half is in the shadow, right? So that means that it is night at that half. Okay, so that's what makes day and night, is this rotation. And to complete a rotation, it takes about 24 hours, right? So that is a full rotation takes 24 hours to rotate around its own axis. Okay, the Earth, right? And as I said, guys, yeah, the Earth's axis is not vertical; it is tilted at 23.5 degrees away from the vertical, right? So this is how it looks like, as I said, and it keeps on rotating, right? It is rotating at this moment, rotating, rotating. So if I would pause for an example in time, let's say we pause this. So this is the sun right over here. I don't know why I've made it tiny, because the sun is very huge. It's actually the earth that is very small. So yeah, I don't mind that. So at any moment in time, okay, this half right over here, as you can see, guys, it is exposed to the sun. This half right over here, it is exposed to the sun, as you can see, right? The sun is right over here, and this half receives the sun's rays, right? It's only this half that receives the sun's rays. The other half is in darkness, right? I will show you this. As I said, guys, I'll show you this in another animation. So because this part receives or is receiving insolation from the sun, so this means that this side, okay, let me just call the side A and then the side B. So side A, because it is receiving insolation, that means that it is daytime here. That means that it is daytime here at A. And because B is in the shadow or is in the darkness and does not receive any light, that means that it is night over here. Right, so that is very important. Okay, I'll talk about the cycle of illumination just now. Right, so let me actually just go on and to show you this. Yes, there we go. So as you can see, guys, at any moment in time, one half of the earth, right, is exposed to the sun. Okay, the sun is right over here. Okay, and by the way, this is another website. This is it's Squirrel, and yeah, you can also check that out. I'll also use this to illustrate seasons. So you have the sun right over here, right, this side, and because the earth is shaped this way, nearly spherical, only one half of this earth will be exposed to light, or will be exposed to the radiation from the sun. So at any moment in time, this part, it's this side, or this half of the earth, it is daytime here, and at this part of the earth it is nighttime. This is in the shadow, right? And mind you, this is constantly rotating, right? Constantly rotating. When it is, let's say this is, if you look at, this is Australia, right? Australia right over here, it is daytime, right? And then if we take a look at Africa right over here, it is definitely nighttime. It is important that we note that. Okay, so rotation is indeed the reason why we have night and day, right? So this side will be exposed to 12 hours of insolation, and this side is exposed to 12 hours of night, of no insolation. So 12 hours, 12 hours, that makes a day, 12 hours where you have day, and 12 hours where you have night, right? Right. So with constant rotation, now you can clearly see that Australia is right over here, okay, because it has rotated that way. Now it is in the shadow, and so it is night here at Sydney in Australia, and this will carry on, and then it becomes day again. So the Earth will keep on rotating. This Sydney, at some point, will be right over there, okay. Will receive the first beams of light, if you may call it that, and that would mark morning, right? And then as it rotates, it will become um 12 p.m., 1 p.m., 3 p.m., so on and so on. And then it becomes 6, 7, and then 8. So it is the night now, and then again and again and again and again. So that's how this occurs, guys. The existence of day and night is due to the rotation of the earth. Okay, while this part of while this half of earth receives uh, insolation, that means that it is day. That part, or that other half of the earth, is receiving no insolation, or is in the darkness, or in the shadow, and so that means that it is night over there. So guys, the occurrence of day and night is due to the earth's rotation. Okay. And we also have, okay, so because now you have this line, okay, the line that separates day and night. Okay, so as you can see, this line right over here, it separates day and then night. So we call that line the circle of illumination. So the circle of illumination is simply a line that separates day and night. It divides earth into day and night. Okay, so that's your circle of illumination right over there. Okay, so yeah, that's the circle of illumination. Even when you look at the South Pole view, you have that circle of illumination. The North Pole view, that's the circle of illumination. So it's simply a line, or an imaginary line, that separates day and night. And then we said parallelism. It is the tendency of the Earth's tilt to remain the same. So I'm not actually gonna write that down. I've actually done so over there. So the tendency of the Earth's tilt to be 23.5 degrees throughout. And I thought that it's also actually important that we remember these. So when we talk about the tropics, okay, we are referring to the places that are close to the equator, right? And there's actually two imaginary lines that serve as a boundary of the tropics. So you have this Tropic of Cancer. You guys do know these. Tropic of Cancer is at 23.4 degrees north, guys. It's north, the Tropic of Cancer, okay? The Tropic of Capricorn is 23.4 degrees south. Okay, it's important to note these lines because we'll talk about these when we are talking seasons, right? So you have the Tropic of Cancer, an imaginary line that marks the end of the tropics in the northern hemisphere, 23.4 degrees north. And then you have the Tropic of Capricorn, which is at 23.4 degrees south, and also marks the end of what we call the tropics, okay, the regions closest to the equator. So please, let's note this, okay? Tropic of Cancer. Okay, so you have Cancer and Capricorn. So I usually recall these as cancer is high. Okay, so the rates of cancer are high, so it should be the highest one, or it should be the one that is in the northern hemisphere, because sometimes you can confuse these two and think that the Tropic of Cancer is right to the south. So yeah, cancer is high, or the rates of cancer are high, and so yeah, Tropic of Cancer should be at the in the northern hemisphere. Okay, let's note that. Now I hope you guys are with me there with the rotation of the Earth, right? It is rotating, right? But now, while it is rotating, as Earth rotates, it also moves around the sun along, okay, that should be along a path called the orbit. Okay, so it is moving along a path that is called the orbit around the sun. Okay, so there's this path over here. I've tried to give you an illustration, guys. So this path right over here, as you can see, we said, guys, Earth is the one that is moving around the sun, not the other way around, right? So this path over here is what we call the orbit. Orbit is a path. It is not a movement. It is a path. Okay, this is the path that the Earth moves along around the sun. That is what is called the orbit, right? The Earth is moving now. Okay, the movement of the Earth. So we're saying that the Earth moves around and around and around the sun like that, right? While it is rotating, right? So it is rotating. Yeah, I couldn't make this rotate. So mind you, it is rotating day and night, day and night, day and night, day and night. While it is rotating, it is moving around. Okay, while rotating, so that is rotation. While rotating, it is actually moving around the sun in this path that we call the orbit. So this movement, moving around the sun, that movement is what we call revolution. Okay, that moving around the sun. Okay, it's going to move around and around and around and around the sun, around and around and around the sun, like that. So that movement is what we call revolution. So while it is rotating, it is revolving. Okay, revolving, we mean it is moving around the sun. Okay, so you have to combine those two movements, okay, to sort of see how it actually moves. So it is rotating while revolving. Okay, revolving or revolution, it is the movement, or it is the Earth's movement around the sun, right? And the Earth's path around the sun is the orbit. Okay, so let's note these guys, right? Because these might sound the same, like the orbit is the Earth's path around the sun, and then the revolution is the Earth's movement around the sun. And it actually takes about 365 days to complete one revolution. Okay, so going from this, okay, let's say it's at this point, right? Going from this point, okay, and moving around like that, moving around and around and around and around and around and around and around, and getting back to the same point, it will take about 365 days. It takes a year. Okay, so a year is simply a revolution. Okay, so it will take 365 days to complete one revolution, while it takes 24 hours to complete one rotation. Okay, so let's note these things, guys. Okay, it's important that we note this. Let me actually show you this movement, right? So I hope you guys can see this. Okay, this is the sun, and that is Earth. Okay, and you can clearly see that Earth is not staying at one point. So this is the orbit, right? Um, that's the orbit right over there, the path that the Earth moves along, and it is rotating while it is moving, right? It is rotating while it is moving. This movement around the sun like that, that is revolution. While that spinning on its own axis, that is what we call rotation. Okay, revolution is the movement around the sun. Spinning on its own axis is rotation. Okay, so that's the combined movement there, guys. While it is rotating, it is actually moving along this path that we call the orbit. Okay, So we have to picture this because it's quite important. Let me actually speed this up. Okay, there we go. So I'll sped this up. So as you can see, it is going, right. It is moving, right. It is moving along this path that is a revolution. It is also spinning on its own axis, and that is um, a rotation. Okay, so please, guys, let's note this movement. Okay, because it's difficult to get these to sort of understand this from a textbook. Okay, how do you actually, and if you're and teachers most of the time, they do not have models or resources to show you how this looks like. Okay, the earth's movement while moving around the sun, it is actually also rotating, right. So moving around the sun, that this is revolution, right. But if you zoom in there, that we know that it is spinning on its axis, so that means that is rotation. These two movements are important because they give us what we call seasons, right. They give us what we call seasons. So at some point, right, due to this revolution and rotation, at some point, one hemisphere, okay, remember, when we talk about hemispheres, guys, talking about a half, okay, half of the earth. Okay, a hemisphere is a half of the earth. So you have the northern hemisphere right over here. So this is the northern half of the earth. That's the northern hemisphere right above the equator, and then you have the southern hemisphere. You note that at some point, if this is the sun, let's say this is the sun right over here. At some point, so let's say this is the sun right over here, and if you look at this clearly, you can clearly see that, well, the northern hemisphere is tilted towards the sun, right. It has sort of bowed to the sun than the southern hemisphere. Can you clearly see that, right? So if I would measure the distance between this and that, so that is much more very close than the distance between the sun and the southern hemisphere, right? So this means that the northern hemisphere at this point receives a lot of insolation, okay, because it is tilted towards the sun. So this means that at this period it receives a lot of insolation, and so this marks what we call the summer. Okay, so because the northern hemisphere at this point is tilted towards the sun, this means that it is summer in the northern hemisphere. The distance is close, right? So it receives a lot of insolation. This is the point where we're going to have longer days and shorter nights. So that means that it is summer in the northern hemisphere at this point. And sometimes they will show you dots that align with the Tropic of Cancer. Okay, if you have a dot that goes straight to dots that align with the Tropic of Cancer, that means that, okay, it is summer in the northern hemisphere. So while it is summer in the northern hemisphere, it is winter in the southern hemisphere, because the southern hemisphere is furthest. It is far, right, from the sun. There's a huge distance there, so it is winter there. So that's why when it is summer in the northern hemisphere, it is winter in the southern hemisphere, right? So we're saying here that it becomes summer in that hemisphere when it is tilted towards the sun. Because this hemisphere is tilted towards the sun, the northern hemisphere, it is summer there. Okay, at some point, remember, it is revolving around the sun, right? So at some point things will look like this, where now you're gonna have the southern hemisphere, right? Okay, so let me zoom in. So because of this revolution, now things have changed. Okay, it's now the southern hemisphere that is tilted towards the sun. So now if we measure the distance again, from here all the way to there, it is much closer than from there all the way to there, right? The northern hemisphere. So now this means that the southern hemisphere at this point, and again, you are going to see dots that align now with the Tropic of Capricorn, right? So this means that it is summer in the southern hemisphere because of the distance, okay, the shorter distance, as we can see. So the southern hemisphere receives most insolation during this period, and then the northern hemisphere, it is winter because it is furthest from the sun. Okay, so it receives less insolation. Okay, so that's how the winter and the summer occur. Okay, it becomes the summer in that hemisphere when that hemisphere is tilted towards the sun. So I will show you this. We're also doing activities, guys. So if you don't get it now, don't worry. So during the summer, there's longer days than nights. During the summer, guys, at 7 a.m. or at 6 a.m., it's already bright outside. So this means that there's longer days. Okay, so because we are exposed to a lot of insolation, so it receives more insolation. That's what we mean when it is summer. Okay, that hemisphere receives more insolation, and then it becomes winter in that hemisphere when that hemisphere is tilted away from the sun. Okay, so as you can see, this is tilted away from the sun. This is far away from the sun. Okay, even if you can look at the distance between those, that's the distance is actually big, right? During the summer, there's shorter days. Okay, at 6 a.m. it's dark. At 7 a.m. it's quite dark. So there's shorter days, really shorter days, and even during the evening at 7 p.m. or 6 p.m. it's already becoming dark. So there's shorter days, quite short days than nights. So that is the winter. So it receives less insolation, that particular hemisphere. Winter means shorter days than nights, and it is caused by a particular hemisphere being tilted away from the sun or having a big distance between it and the sun. And this period, I don't know what's wrong with my spelling today. So, this period of unequal days where there is shorter days than nights or longer days than nights, we call that a solstice. Okay, so a solstice is a period of unequal days. Okay, whether it's longer days than nights or shorter days than nights, they are just not equal. Okay, so this means that summer is an example of a solstice. Okay, summer solstice, that's what we call it. And during summer solstice, as of course you guys know, there's longer days than nights, and during a winter solstice there's shorter days than nights. Okay, so yeah, that is important to know, that a solstice is a period of unequal days and nights. And in the southern hemisphere, actually, we have summer solstice on the 21st of December. This date marks the start of summer, okay, the beginning of summer, right? And our winter solstice is on the 21st of June, right? So summer solstice, we have longer days than nights from this day, the 21st of December. Okay, in the southern hemisphere, guys, because it is the opposite in the northern hemisphere. Because on the 21st of December in the northern hemisphere, that's the start of their winter solstice, while it is the start of our summer solstice. Okay, so it is so it's important to note that. Okay, because they can ask about the northern hemisphere or the southern hemisphere, so you have to really think about it. And it is winter solstice for us on the 21st of June in the southern hemisphere. It is in the southern hemisphere, and it is summer solstice for them in the northern hemisphere on the 21st of June. Okay, so this is vice versa in the northern hemisphere. Okay, so let me actually just show you guys. Let me see if I can show you something. Okay, so like for an example, guys, during this period, you can clearly see that the northern hemisphere is tilted towards the sun, right? It's the northern hemisphere that is tilted towards the sun. So, yes, we can see that rotation. We can clearly see that the northern hemisphere, because it is tilted towards the sun, it receives most of the insolation. So, that should mark summer. Let me actually show you another example. Now, guys, can you take a look at this? Okay. Do you see position number one, right? So, position number one, take a look at the view. Okay. So, this is the view, right? So right over here, you can clearly see that it's the northern hemisphere that is tilted towards the sun, right? So what does that mean? This means that the northern hemisphere receives most of the insolation. This marks the summer for the northern hemisphere. Now I'm going to shift this and move this or revolve the earth until it's now the southern hemisphere that receives most of the insolation. Okay, let's go. Okay, we're going. Yes, going and going and going. We'll talk about number 4, number 2. Now look at this, okay? right at this position, guys, what is happening now? Okay, at this position is the southern hemisphere that is tilted towards the sun. So it's the southern hemisphere that is receiving most of the insolation. This means that it is summer in the southern hemisphere and winter in the northern hemisphere. And at this position, this means that it is summer in the northern hemisphere and winter in the southern hemisphere, because the southern hemisphere is a big distance away from the sun. It is tilted away from the sun, and the northern hemisphere here is tilted towards the sun. So it is summer in the northern hemisphere here and winter in the southern hemisphere. And moving or revolving the earth like that means that at this point it is summer in the southern hemisphere, because it is the southern hemisphere now that is pointed or that is tilted towards the sun, and it is winter in the northern hemisphere. Okay, so that's how we should look at this. That's exactly how it looks like. I'll also try to do this here again. Let's see, let me just actually delete that, right? So again, because of the revolution, guys, let's start over here, right? Okay, let me actually delete these. So because of the revolution at this point, so this is point number one, because the earth revolves, right? So this is point number one. So at this point, you can clearly see that it is the northern hemisphere that is tilted towards the sun, right? And then I move. I will talk about this point. So at this point, you cannot really say that it is the southern hemisphere or the northern hemisphere that is tilted towards the sun, right? What about at this point? So at this point now, you can clearly see that, okay, it's the southern hemisphere that is tilted towards the sun. So it is summer solstice in the for the southern hemisphere, and winter solstice for the northern hemisphere at that point. Okay, so at point number two, guys, this is important to note. Okay, very important to note. Please let me know if you did not understand this. I will definitely do another video just focusing on this. Okay, so as I said, when it is summer solstice in the southern hemisphere, it is winter solstice in the northern hemisphere, so on and so on. Okay, but you have to know that on the 21st of December it is summer solstice in the southern hemisphere, and on the 21st of June it is winter solstice in the southern hemisphere, right? And then it's the opposite for the northern hemisphere. Now there are periods of equal insolation received. Both the hemispheres receive the same amount of insolation, and this is because neither one of them is tilted towards the sun. Okay, and that period is what we call the equinox. So equinox is simply a period of equal insolation for both hemispheres. Okay, so equinox, equal insolation. Okay, and this goes for autumn and spring. Okay, so during autumn and spring, both hemispheres receive roughly the same amount of insolation. So no longer day or shorter day, the same number of hours for day and same number of hours for night. So 12 hours each. 12 hours for day, 12 hours for night, not a longer day and shorter. That is what we call equinox. Whereas solstice, period of unequal day, whether it's longer nights or shorter days, or shorter nights or longer days, that is solstice. But for equinox, it's the same amount of insolation, meaning the same hours of insolation. So 12 hours for both day and night. And yeah, in the southern hemisphere, we have autumn equinox on the 21st of March. So that's what begins or marks the beginning of autumn. Okay, in the northern hemisphere, it is their spring equinox. Okay, on this 21st of March, we have spring equinox on the 21st of September. This marks the beginning or the start of spring season, the 21st of September. And again, during this time in the northern hemisphere, it's their autumn equinox. So yeah, this vice versa in the northern hemisphere. So during spring and during autumn, these are periods or these are seasons where both hemispheres receive the same amount of insolation. So the same hours of day and same hours of night. So 12 hours, 12 hours. That is equinox. And in this case, so let me just show you this. So if you can, let's say, let's take a look at this. If you take a look at this, let's say right over here. Okay. So at this point, so for an example, at this point, guys, the northern hemisphere, right? If you can take a look at the northern hemisphere, it is tilted that way, right? And the southern hemisphere is tilted that way. So neither one of them are tilted towards the sun. Okay. So this means that they receive the same amount of insolation. Okay. All of this insolation is going to both of them like that. Okay. Neither one is tilted towards the sun. Okay. So this is an equinox. Definitely should be an equinox. Okay. Where on here, right over here, you can clearly see again, you use the same arrows there. You can clearly see that it's the northern hemisphere that is tilted towards the sun, and so it is the summer in the northern hemisphere and winter in the southern hemisphere, right? So, and yes, at this point again, we move again. This is tilted that side, and this is tilted this side. So again, right over here, guys, you can clearly see that, okay, neither one of them, again, is tilted towards the sun. So this means that they receive the same amount of insolation again. So this is an equinox. So number 3 and number 4 marks the equinoxes. And then number 1 and number 2 mark the solstices, right? So number 2 in the southern hemisphere, it is the summer solstice, and winter solstice in the northern hemisphere, and yeah, so on and so on. So this is important to note, very important to note. And if you think about it, for us in the southern hemisphere, right, after summer, which season comes next? After summer, it is autumn, right? So it is our autumn here. It is the autumn equinox for the southern hemisphere. This means that this is 21 of March. Okay, autumn equinox for the southern hemisphere, and spring equinox for the northern hemisphere, right? Then so on and so on. This is our winter here, guys. Okay, because southern hemisphere is tilted away from the sun, right? So this is our winter equinox. This is the 21st of June. And after winter, we know that there's spring. So this is our spring equinox, the 21st of September. And yes, going again at position number 2, this, we are tilted towards the sun. So this is the 21st of December. So guys, let's really be smart about this. Yeah, let's fully understand it, guys. So I hope you guys can see that. So that's how seasons occur, guys. Okay, it's because of the rotation and revolution. Okay, rotation and revolution causes seasons, and seasons are another reason for unequal heating. Okay, we talked about latitudes, okay, being the first reason for unequal heating. And then now it's seasons, because if you're saying that on the 21st of December, the southern hemisphere receives most of the insolation, that means it receives most of the energy. So the energy is now concentrated right over here in the southern hemisphere, and it is cold in the northern hemisphere. Okay, so you can clearly see that the energy now is not the same. There's an energy imbalance there. So due to the seasons, we receive different amounts of heating. So this means that there are 2 factors that affect the amount of insolation that we receive. Number 1 is the latitude. Number 2, it's the seasons. Okay, that's the whole point of this video, guys. But of course, the concepts that I talked about, that I touched on here, are important. So seasons mean different parts of the earth receive different amounts of insolation throughout the year, throughout the revolution, as we said, and hence seasons contribute to unequal heating of the earth. And we also say the amount of insolation on earth, or the amount of insolation earth receives, depends on latitude, and seasons. They like to ask this a lot, so I thought I should write that down. We are going to head on to activities, right? We'll just do a couple of activities just quickly. Okay, so let me zoom in here. Now I got this from Stanmore Physics, I think. Supposed to match the descriptions on column A with the concepts or the terms on column B. So I'll write to 1.1.1 says the angle of the Earth's axis as the Earth revolves. Okay, the angle of the Earth's axis as the Earth revolves. So I'm supposed to choose between Y or Z and Z. So what do we call that angle of the Earth's axis as the Earth revolves? We call that the tilt. Earth's tilt, as we said, guys. So we are going for Y for 1.1.1. So that is the Earth's tilt. And 1.1.2 says the movement of the Earth around the sun. Okay, the movement of the Earth. It's important. The movement of the Earth, not the path of the Earth. So the movement of the Earth is what we call the revolution, guys. Cannot be the orbit. Orbit is the path of the Earth around the sun. Okay, so we're going for Y for 1.1.2, and then 1.1.3 incoming solar radiation. We know this from grade 10. Coming solar radiation is insolation, not insulation. Insulation is another concept. So insolation, going for Y again for 1.1.3. And then 1.1.4 says the path that the Earth travels around the sun. Okay, I don't know if you guys see. Can I zoom in? So the path of the Earth, the path that the Earth travels around the sun. The path, so that is orbit, guys. Okay, remember orbit is the path, movement is the revolution. So we're going for Z for 1.1.4, 1.1.5, radiation from the Earth. So the Earth also gives out its own energy, and it's a long wave radiation that we call terrestrial radiation. So 1.1.5, we're going for Z. Shortwave radiation, guys, is solar radiation. Long wave radiation is terrestrial radiation. And then when one hemisphere is tilted towards the sun on the 21st of December, okay, and that hemisphere should be the southern hemisphere, right? Tilted towards the sun on the 21st of December. Yeah, that should be the southern hemisphere. And that is a solstice, guys, because, well, this is summer, right? When it is tilted towards the sun, this is summer. So summer has longer days than nights, so unequal days and nights. That's a solstice. So we're going for Z for 1.1.6, then 1.1.7. The line, when neither hemispheres is tilted towards or away from the sun. Neither of them, none. So that is equinox, definitely, guys. So why? None of them are tilted towards the sun. 1.1.8, so they receive the same amount of insolation. Line between light and dark halves of the Earth. Okay, we talked about that. What is that line that divides the Earth into day and night? That is the circle of illumination. So 1.1.8 is circle of illumination, guys. And yeah, let's carry on. Let's move. Okay, so right over here we have, and guys, with questions, you can never rush like I'm doing right now, okay? Please do not rush. Please take your time, okay, to fully understand the question. So I'm going to read out the figure 1.1.1. The angle at which the sun's rays strike the earth, okay? Angle at which sun's rays strike the earth. So we have A over here, right? So I'm just interpreting this diagram, and you can clearly see that A, there's a short distance from there, from the sun to there, right? And number two, the solar energy is concentrated over a small area compared to over here. B is concentrated over a larger area, right? So yeah, these are the reasons why the equator receives more energy or receives more insolation than the poles. 1.1 says at which place do the sun's rays pass through a larger atmosphere than the other? Okay, which place do the sun's rays pass through a larger atmosphere than the other? Okay, so because this is far away, okay, if you can take a look at this is far away and it's covering a large distance, a large area. I'm sorry about that. And so a wide area that it covers, a wide atmosphere that it covers, right? This is a little bit of atmosphere, right? That is a huge amount of atmosphere, okay? So that should be B, okay? The sun's rays pass through a larger atmosphere, yeah, here at B. So 1.1.1, we're going for B. And then 1.1.2, where do the sun's rays spread over a larger surface? This one, okay? So this is a larger surface, guys. Okay, from there to there, compare that from here to there. Okay, I hope you can see these lines. That means that it's B, right? So we're going for B. This is where the sun's rays are spread over a large area. And then 1.1.3 says, at which place will the atmosphere be more intensely heated? Well, it will be more intensely heated at A, right? That's intense heating. Due to direct sun rays, number one. Number two, sun's rays are concentrated over a small area. Remember those reasons, guys. They are going to be asked. I'm telling you. Why is the equator warmer than the poles? I'm telling you. 1.1.4 says a place with higher albedo. Okay, a place with higher albedo. Okay, where is snow, guys? Where is snow? Snow is at B, right? So at the poles. So snow reflects a lot of the sun's rays. So it has a high albedo. 1.1.5 says a place where the sun's rays strike the earth at 90 degrees. Okay, we talked about that and we said that is A, right? They strike it at 90 degree, at a 90-degree angle. Okay. Yeah, I'm sorry about that, but yeah, it is a not at an oblique angle. Yeah, at 90 degrees or perpendicular. 1.1.6 says the sun travels a longer distance before reaching this place. Yeah, B, definitely. This is a longer distance than at a shorter distance, right? So sun's rays travel a longer distance at B. So we're going for B for 1.1.6. And then 1.1.7, this place receives insolation throughout the year. I talked about that a little bit, and that is the equator. Equator receives insolation throughout the year, guys. The most insolation is received at the equator, so that is A. Whether it is summer or winter or spring or what, it receives the most insolation. Here's another one. So right over here, we clearly see, let me actually zoom in. I don't know if you guys can see this, but there are dots right over here. Can you see these dots? And these dots align with what? They align with the Tropic of what? Of Cancer. Okay. So what does this mean? Okay. So the northern hemisphere, right over here, that's the northern hemisphere, is tilted towards the sun. Okay. And by the way, guys, sorry about that. I did not mention this. The sun, even though I did not really say that, the earth, I mean, rotates like this. Okay, it moves. It really depends where you're looking at this from. If you're looking at this from the the northern pole, you're going to see that the earth rotates anti-clockwise, and from the south pole it rotates clockwise. But yeah, the rotation is, yeah, it goes that way. And this is the reason why the sun looks like it is rising from the east, is because we are going to the east. Okay, and yeah, okay, imagine this is the darkness and we are going this side. We're going to see the sun like it is moving this side, right? Because we are moving that side. So that's why we're saying that it is rising from the east, the sun. All right. So 1.1.1 says the season the southern hemisphere experiences is what? Season the southern hemisphere experiences. Well, if the northern hemisphere experiences summer, the southern hemisphere should experience winter. So it should be winter here, guys, for 1.1.1. 1.1.2 says the arrows at A shows the dash of the Earth. The arrows at A, the arrows, oh, okay, the arrows, oh, they show rotation, right? They show the what? Not the circle of illumination, not the evil revolution, or the no. They show the rotation. Okay, the Earth is rotating. That's what makes our day and night. And 1.1.3, the sketch illustrates a or an dash situation with the days being dash than to the night at the equator. Okay, the sketch illustrates what situation? Well, first of all, the sketch illustrates a solstice, guys. Okay, because well, it is summer there, it is winter there. So that's a solstice, number one. Okay, it represents a solstice with the days being dash than to the night. Okay, at the equator. Now let's note this: at the equator. At the equator, guys, the days will always be equal. Always be equal, whether it's summer on what or what. At the equator, this will always be equal. So yes, it is a solstice, but because we're talking about the equator, though, it should be equal. Okay, it doesn't matter whether it's winter or what. 1.1.4 says line BC represents the dash of the Earth's axis and is dashed throughout the year. So line BC, where's line BC? Line BC represents the axis, right? Right, it represents the axis, or you can say it represents parallelism. And this parallelism is dashed throughout the year. It is consistent, it is the same throughout the year. So it's Roman figure 2 and 3. So that is C. 1.1.5, the amount of insolation that the Earth receives depends on dash and dash. Talked about that, guys. It depends on only the latitude and the seasons. Okay, not anything else. So Roman figure 1 and Roman figure 3. So that means we are going for A for 1.1.5. Right. Yeah, let me know, guys, what you think of my answers there and what you suggest. We are a community, a learning community, and we cannot learn without any mistakes. If I've made any mistake there, please let me know and please explain that to me. Okay, and I will fix that. Now, guys, thank you for tuning in, and please like, subscribe, share. That's how I'm going to release more and more and more videos. Okay, I'm going to upload more videos if you guys subscribe, if you guys share this content to your friends and family, to your peers at school, right, to your teachers, so on and so on. So let's carry on. Let's build this family. Let's grow as a grade 11 geography community. And I wish you all the best for this year. Let's start it on a strong note and let's carry on strong, right? So thank you again, guys, for tuning in. And I'm going to see you in the next one.